For part 3 of chapter 6, we have now gotten into the world of quantum theory, and this video will be all about assigning quantum numbers so that we can describe the different quantized energy states that electrons can exist within. Okay, so to set the stage where we left off on the previous video, right, in the macroscopic realm where we exist, particles and waves behave differently, right? Throwing a football, thinking about a particle, behaves very differently from a wave of, say, water at the beach. Okay, but our first two videos told us that in the subatomic realm, we have a different set of rules, right? In our microscopic world, waves and particles are no longer separate, which we saw before with light. So that brings us to quantum mechanics. Okay, we talked about the Bohr model before. Many famous scientists were involved in this development of quantum mechanics, right? We had Bohr, we had Einstein, we have Schrödinger, de Broglie, Heisenberg. This gave us a new field of quantum mechanics, which is important to develop in our understanding of chemistry and the behavior of electrons. Okay? Electrons can exist only in discrete energy levels, right? We talked about steps in the previous videos. They can exist on those steps, but not between them. And we say that the energy of these electrons are quantized. Okay? Electrons can exist in specific quantized energy states. They can only jump between those states. And that's why we saw a specific absorption spectra, line spectra, okay? Not a continuum of energy. It's not a smooth transition. It's done stepwise. So we need a way to describe these values, and that's done with quantum numbers. And we'll spend the rest of the video talking about quantum numbers. There's a set of 4 quantum numbers that you can use to describe any electron, and they are as follows. Okay, we'll start with N, okay, then we go to L is in Larry, and then M sub L, and then M sub S. Okay, those last two are M is in monkey. So our first quantum number, N, is in Nancy. That's called our principal quantum number, also known as the shell number. Okay, and this talks about our energy level. Okay, if we think about the shells of an atom being kind of concentric circles, getting larger and larger and larger, radiating out from the nucleus, this is what our N helps describe. Okay, the larger the value of N, the higher the energy of the electron. Okay, so as N goes up, the energy increases as well. Okay, again, N is known as the principal quantum number. Talks about the location of our energy levels, kind of like what we were talking about in the Bohr model before. So what's our rule for referring to N? And there will be 4 of these slides in this video, and you will definitely, without a doubt, want to know these slides where they're labeled rule. And this is our rule for N, the principal quantum number. It must have an integer value, must be positive. And so it has to be greater than 0. It can be 1, 2, 3, 4, 5, 6, 7 is typically the highest principal quantum number we see. In theory, it could be higher as well, 8, 9, 10, but we typically see those values, 1, 2, 3, 4, 5, 6, 7. And this is just a picture representation of what those mean, right? The higher that number gets, the further away it is from the nucleus. And as we mentioned before, the further away from the nucleus, the higher energy those electrons are. So that's what our principal quantum number describes. How about atomic orbitals? Yep. Principal quantum number starts to describe what's known as an atomic orbital. Okay. What is an atomic orbital? Okay. It's a region of electron density. Okay, and it's not just a line going around the nucleus like what we would have seen right here in this representation, right? It's a 3-dimensional region of probability. And these things are based on mathematical solutions to what's known as the Schrödinger equation. And this orbital is just a region of probability, right? It's where that electron is most likely to be. Okay? And an atomic orbital is different from an orbit where something's just going around, right? It's a region in 3D, right? Region of 3D density. And this quantum mechanical model has told us where those regions of probability are. And that describes an atomic orbital. We use 3 quantum numbers to describe an atomic orbital. Principal quantum number is 1, that talks about the energy, but we have 2 others as well that are describing atomic orbitals. That brings us to our second quantum number, which is known as the angular momentum quantum number, represented by L. Okay. That also carries on integer values. That talks about the shape of the orbital. So N told us about the energy, L tells us about the shape. Okay. The values that L can possibly have is anything from 0 on the low end. Okay, so L can also not be negative. The lowest it can be is 0, and it can take on any value up until n minus 1. Okay, so you have to know n before you can determine all the possible values for L. Because if n is equal to 1, for example, L can only be 0 because it maxes out at n minus 1. If n is equal to 2, L can be 0, L can also be 1. Those are 2 different orbitals. Okay. If something has an n equal to 5, okay, L could be 0, 1, 2, 3, or 4. Okay. Later on, we'll talk about subshells, and that's where we have things that have the same value of L. Okay. Same value of L. That gives us a subshell. We'll talk about those in a couple slides. Here's our rule for L. We said before, it's the angular momentum quantum number. It depends on n. Can't be negative, okay, but it can be 0, and that's different from n. Right? N cannot be 0 or negative. L can't be negative, can be 0. Okay, so any integer value for L up to n minus 1, summarized nice right here. Okay, 0 less than or equal to L, less than or equal to n minus 1. Okay, and just to give you an idea of what these things look like, I'm going to jump ahead a couple slides. These are what our orbital shapes are. Okay? Described by different values of L. This is an L value of 0, L value of 1, L value of 2, L value of 3 down here. As you can see, those have some pretty different shapes. But we'll get to that slide 50 here in a second. Okay, we left off right here on 44, so going to 45 now. What we typically do is, instead of using the number value for L to talk about the shape of those orbitals, we can define the angular momentum quantum number also with a letter. And I do expect you to know these 4 right here. If an L is equal to 0, that's called an s orbital. L is equal to 1, that's called a p orbital. L is equal to 2, that's called a d orbital. L equal to 3 is called an f orbital. And after that, they do exist in theory, nothing we see on the periodic table, and they're just alphabetical. L is equal to 4 would be G, L is equal to 5 would be H, etc. And you may have noticed looking at those shapes, right? If not, you can check your notes, slide 54, on by my count anyway, with those different shapes. Might be slightly different in your notes. Right? Remember, these are regions of probability. Okay? So there are certain distances from the nuclei where the probability of finding the electron is 0. There's no chance you find it there. Okay? That's defined, remember, these are solutions to an equation. That tells us the wave function value is 0 at that distance. Okay, we don't have to know about the solutions, just know the definition of what that is. It's called a radial node. A certain distance from the nucleus where the probability of finding an electron is 0. That's called a radial node. And we should be able to know how to predict those. Okay. How many radial nodes do we have? Well, once you know the value of n and L, you take n minus L minus 1. That's how many nodes you have. So for example, if you have something that's 1s, okay, 1 is the principal quantum number, n. S tells you the L value is 0. We just defined those. Okay, so 1 minus 0 minus 1 from up here tells us there's no nodes there. And there's 2 examples as well. What do they look like as a picture, right? There are 0 nodes over here. Notice right here that gap between the blue and the pink, right? That's a radial node. This one has 2 of them. There's a gap here and a larger gap there. Okay. Probability of 0. You see it right here as a probability function. It is hit 0. Those are called radial nodes. What are these specific shapes? Once I know the L value, okay, if something is an S orbital, meaning it has an L value of 0, we just saw a couple of those. Those are spherical, okay, nice sphere. If something is a P subshell, it has an L value of 1, okay, those have a dumbbell shape. D and F orbitals, as we'll see on the next slide again, get a little more complex. Okay? But you should know that S is spherical, P is dumbbell. Yep. Again, 3-dimensional regions of probability. And here's this slide again, showing those shapes. We referred to them by their L values before. Okay? This was an L value of 0, now called an S orbital. These are L values of 1. Notice they're called P orbitals. We'll talk about the other things next. L value of 2, D orbitals. L value of 3, F orbitals. But what about, notice the X, Y, and Z here on those? That brings us to our third quantum number, which is the magnetic quantum number. Okay? And the whole reason for the magnetic quantum number is because for all of these other orbitals, right, as long as it's not a sphere, they can point in different directions. And the magnetic quantum number tells you the orientation of the orbital in space. Because if I have a p orbital that's dumbbell shaped, right, it can point along 3 different axes, the x-axis, the y-axis, and the z-axis. So if you can think about that, you have the same energy if you're standing up or if you're laying down forward and backward or laying down left and right. Those are all the same energy, but we point different directions. Those are different orbitals. And that's what the magnetic quantum number describes. Just like L is based on N, the magnetic quantum number, which is represented by M subscript L, it depends on L. And M sub L can have negative values. It can have any value between negative L and positive L, including 0. So that depends on what our L value is, right? If L is equal to 0, then M sub L can only be 0 because there's nothing between negative 0 and positive 0. But if L is equal to 1, there are 3 possible M sub L's, -1, 0, +1. If L is 2, there are 5 possibilities between negative L and positive L, right? -2, -1, 0, +1, +2. If L is equal to 3, there's 7 possibilities. -3, -2, -1, 0, +1, +2, +3. So that's all summarized nice on this slide right here. M sub L is between negative L and positive L, right? Or saying it a different way, negative L less than or equal to M sub L less than or equal to positive L. If I'm quickly referring to a orbital, I don't need to worry as much about the magnetic quantum number because I'm just thinking about all of them simultaneously. That subshell that I referred to before encompasses all of the different directions. So if I'm quickly referring to an orbital, I just say the N and the L value using the letter designation for the L. Okay, so I can quickly refer to an orbital by saying something like 2s or 3p. If I say that, you can pick up N is equal to 2, L is equal to 0. We get that from the letter S. Over here, N is equal to 3, L is equal to 1 in 3p. Okay? And we can do that because those things all have the same energy. They're just pointing different directions. And that's called degeneracy. Okay? All the energy levels with the same principal quantum number are called degenerate energy levels. Okay? Now, if we have multiple electrons, it gets a little trickier, okay, because we also have those electron-electron interactions to account for, one of the things the Bohr model did not, right? But as long as I'm within the same subshell, it's still containing the same energy. But now if I change the letter, they have different energies. So what does that look like graphically? Okay, over here, right, 1s, it only has one value of m sub l, just one orbital here. It's got the lowest energy. And then I know if I increase the principal quantum number, the energy goes up, right? 1 to 2, 2 to 3, 3 to 4. But within something like the 2p, the 3p, or the 3d, or the 4p over here, right? These are degenerate energy levels. Notice they all have the same E value, right? The 2p's, the 3p's, because they have different directions, sure, but they're all in the same subshell. They have degenerate energy levels. They are the same. So how about our fourth quantum number? Okay. The first three quantum numbers are what we are using to describe the orbitals specifically, these regions of probability, three-dimensional region of space. Okay, but the electron spin is described by the spin quantum number, and that's a little bit of a different kind of property. Okay. What it describes, in a little bit of an oversimplification, is how the electron rotates or spins within the orbital itself. And an electron can only spin in one of two quantized states. That's it. It can only do it one of two ways. A oversimplification way to think about it is like a clock, for example. Okay? It's locked into space. It can only go clockwise or counterclockwise. That's it. Okay. So the spin quantum number, which is our fourth and final quantum number, is represented by m sub s. And rule 4 here, this is the fourth rule slide, it can only exist in two possible values. M sub s is equal to plus 1/2 or minus 1/2. No other values are possible for m sub s. Right, so anything else, 0, doesn't work. Minus 1 doesn't work. Plus 2 doesn't work. It can only be plus 1/2 or minus 1/2. Okay, because it can only have those two values of spin, which we described before and which are shown here. So that brings together four quantum numbers, N, L, M sub L, and M sub S. Why is this useful to us? Brings us to what's known, a really important concept for this chapter, the Pauli exclusion principle, right? Named after Wolfgang Pauli. If we are using four quantum numbers to describe an electron, right? N, L, M sub L, and M sub S. They are always listed in that order. The Pauli exclusion principle tells us that we have to have a unique set of quantum numbers to describe every electron. So the way the Pauli exclusion principle is written states that no two electrons in the same atom can have exactly the same set of all four quantum numbers, because that would be redundant. Okay? We need to describe every electron uniquely. Okay? Can't have the same set to describe two things. Right? That would be like two students in the classroom being referred to by the exact same name. We have to have a unique set of quantum numbers. So it is possible that the first three, N, L, and M sub L, are all the same. Okay? But if that's the case, only two electrons can do that, because M sub S can only be plus 1/2 or minus 1/2. You can never have the same set of all four quantum numbers representing two electrons. Yep. Which is what the top of this slide was referring to. Another way to state that is that no more than two electrons can occupy the same orbital. Every orbital maxes out at two electrons. It can take the plus 1/2, it can take the minus 1/2, but no more. Okay? And if those two electrons are in the same orbital, they have to have opposite spins. One's going the clockwise, one's going the counterclockwise way. all of the information from this video, except for the Pauli exclusion principle we just mentioned, is nicely summarized on this table right here. This summarizes all the quantum numbers. This is a huge bit of information from chapter 6. So I would suggest that you memorize this slide. It kind of ties together all the rules we mentioned before. It talks about the principal quantum number, angular momentum, L, magnetic quantum, M sub L, spin quantum, M sub S. What their name is, what their symbol is, their allowed values. Okay, particularly this bit in the middle is what you should be able to tell, right? The symbol and what their allowed values are, as well as the letter representation, quickly referring to something as like the 4D subshell, right? Or the 2P subshell, any one of those. So good practice here at the end of the video now is to identify the subshell, right, with the letter notation where the following quantum numbers found. N is equal to 3, L is equal to 1, and then answer how many electrons are possible to have that quantum numbers. And then even better practice, to take it a step further, is to write out the set of quantum numbers for each one of those possible electrons, and I will upload a video separately showing how to do that. Yep. The only other note is when you are writing out your quantum numbers, you do them in between those type of brackets. Okay, apologies for the drawing here. All right, but you put those brackets and then they go in order after that. N, L, M sub L, and M sub S. You always list them in that order between those brackets. Okay. I'll upload a separate video with this answer later on, okay, but make sure you try this on your own. Then later on, we will have following videos using these numbers plus orbital diagrams.